So this is the three-dimensional box or three-dimensional version of the particle in a box, and three-dimensional box mean now we are going to consider the x-axis, y-axis, and the z-axis. So this is the three-dimensional box, and this is actually the cubic box over here. In a similar way, as we have discussed the potential energy in case of the one-dimensional box and the two-dimensional box. Here, the limits are also given over here. When the particle is in the box, and the potential energy would be zero within the box, and it would be infinity out of the box. And because the particle is confined on the one of the surface over here along the x-axis, y-axis, and the z-axis. So these are the lengths are given over here. In a similar way, you can say this is if the particle is moving along the x-axis, this is the length of the box Lx, the length of the box along the x-axis. And as we have mentioned in two-dimensional box, you may differentiate between the x, y, and z by putting the 1 for the x-axis, 2 for the y-axis, and 3 for the z-axis. Or you may put the x, y, z. It is up to you what is more convenient to use to differentiate between all the three axes. So this is the particle, the movement of the particle along the x-axis, having the length of this is Lx, and the movement of the particle along the y-axis, and this is the length of the box along the y-axis. And in a similar way, this is the z-axis, and this is the length of the box along the z-axis. So when the particle is in between the box, the potential energy will be equal to zero, and when it crosses the limits of the box, then potential energy will go to the infinity. And this is the same explanation as I have explained in particle in one-dimensional box and the two-dimensional box. So that's why the previous knowledge of the is very important to understand the these concept, or the coming more complicated concept to understand what would be the Schrodinger wave equation and its solution with the three-dimensional version of the box. So this is the, now I'm just showing the last version, the particle in three-dimensional box. This we have discussed the solution of the Schrodinger wave equation along the x-axis. It was equal to this, and by using the wave function, the total wave function of a particle along the x, y, and the z-axis with the quantum numbers of n1, n2, and 3. These are the nth energy level, and 1 is indicating the x-axis, and 2 is indicating the y-axis, and 3 is indicating the z-axis. It doesn't mean the value of n1 is 1 or value of n2 is 2. This is not the case. This one and 1 and 2 and 3 are just indicating the x, y, and z axis, and the values may be different, or maybe n1 is having the value 1, and this n2 is having the value 3, or n3 is having the value 2 or 1, and even 3. So it depends what would be the transition of the electron or the particle along the x and the y and the z axis. So here, just this is the product of the wave function along the x-axis, y-axis, and the z-axis. So you have to multiply 3 times by considering this equation, one time along the x-axis, then with the y-axis and the z-axis. So what would be the difference? This is the L1. Again, very simple to understand. When you are using the X, the value would be 1, 1, and the 1 over here. When you put the along the y-axis over here, then this value would be 2, this value would be 2. When you put the z-axis, this would be 3 and 3. Even you can put z over along this side. Actually, this is just to differentiate between L1 with the L2 when you are using a one of the axes over here. So you this is the product of uh, x, y, and z. You have to multiply this factor by the 3 times. So 2 multiplied by 2 multiplied by 2, that would be equal to 8. And L1 multiplied by L2, L multiplied by L3. And this is the under root coming from the equation. And now you have to multiply this along the x, y, and z axis. So sine and 1 pi x over L1, and then sine and 2 pi y over L2, because this is y, that's why you are just differentiating the n and L by putting with the figure with the value 2 and uh, just labeling it with the 2 with the n and the L. And for the z-axis, you just going to differentiate among the other one by using the pi z, and when this is z, that will be the n3 and the L3. So simply this is the product of the wave function along the x-axis, y-axis, and the z-axis. So this is all the total wave function of a particle in a three-dimensional box, and these are the limit. The limit will remain the same. We are using over here the along the x-axis. This would be the less than L1 and greater than 0. Similarly, along the y-axis, this would be less than L2, greater than 0, and the z-axis would also be less than L3, greater than 0. That means the particle should be confined within the box, and that would be the total wave function of the particle moving along the three axes. And what would be the total energy? Total energy would be the sum of the uh, energy along the x-axis, y-axis, and the z-axis. And the same equation like we are using over here, you can use the particle in one dimension box. This was the n square h square over 8ml square. So in a similar way, we have done with the particle in two-dimensional box. So you just increasing one of the more factor over here, and it would be the n3 square over L3 square. And this we have mentioned over here. So this is the total kinetic energy of a particle moving along the three axis. So this is all about the particle in three-dimensional box, and we have done with the movement of the particle in very detail when it is moving along the x-axis, y-axis, and the z-axis. And these equations are very useful, particularly for the computational chemistry or the computational science, to calculate the energy or the absorption spectra uh, when the particle is moving along the any of the three axes. And we have already done some of the calculation in one of the previous lecture. So this is the end of this lecture.